and I'm happy to share with you a few tips and tricks to optimize your Kafka for better cost efficiency and performance. After me, Victor, which I'm personally super excited to hear his lecture as well. So worth waiting also. And yeah, let's start. Would be awesome if it will be sort of like an ongoing Q&A type of discussion. So please stop me wherever in any part of the deck. Would be great to make it sort of like an interactive session rather than just a lecture. So let's start. Just to create a baseline, what is Kafka? Because Kafka has so many use cases, and explaining Kafka to one might not make sense for others. So I always say, like, if someone asks me like, what is Kafka? Because not everyone has the maturity with Kafka than we would think. So Kafka is many things at the same time. It can be a real-time database. It can be a queue. And the official term is like an event streaming platform. So it serves so many different use cases. That's what makes that component and that infrastructure for me super interesting. And while built for scale, and that was the initial thought behind creating Kafka, to serve high velocity, large scale, big data use cases. These days, Kafka supports workloads and companies of all sizes. So you can find it supports asynchronous communication between microservices, even a few microservices, not like hundreds and stuff. And it was not like that at the beginning, but right now with the maturity of Kafka and the popularity that it gained, it definitely supports basically all types of workloads. And why optimization? Why we need to optimize our Kafka, and why now? I think it's the most important question. Why to think about it right now? So 80% in, 20% out. My theory, which I started with like 3 years ago, was that right now, within everyone's organization, 80% of the data that goes into our company or to our environment, 20% actually preserved and being queried and indexed and fetched, while 80% is mostly go to some archiving, if not dropped. And right now we see sort of like the other way, where 80% of the data, because of all the ML and AI maturity and all the use cases that arise from that, we see a different case where 80% of the data gets stored in a way that it needs to be analyzed, fetched, and queried, and only 20% gets archived or thrown. And that's a very, very big shift. And Kafka is the centerpiece that supports data streaming, that empowers that scale. And so if we want to do that, or we want to use Kafka in order to do data streaming in that scale, it needs to be optimized. Otherwise, we will break our bank. So 80% in, 20% out. Data, yeah, a lot more data and a lot more complex. It used to be JSONs, it used to be XML, it used to be text. Right now it's like protobuf, AVO, different types of indentations and more complicated events than it was before. And we need to get that data a lot faster than we used to before. And yeah, it all sums up with the economic situation in the world, that we supposed or we require to do things in much more cost efficient way, and to maintain cost efficiency in every angle, every aspect of the development lifecycle, and specifically in our infrastructure. So that's why it's so critical to think about it now and take proper measurements. Let's start with cost, and then we'll switch to performance. And again, I'll repeat what, like, the thing that I'm about to say repeatedly throughout the lecture. There is no silver bullet. There is no rule of thumb for making your Kafka cost efficient or performant than it is right now, because Each cluster, each company, each environment, each application has different patterns, different workloads types, different message sizes. So there is no silver bullet for one. And if we will try to do a one size fit all solution or tuning or optimization, we might even damage our environment. So just keep that in mind and make sure that you do proper testings before taking any action that you will see in this in my lecture at least, or in the tips that I'm about to show you. So I try to keep that as high level as possible and really focus on the tips, on the optimizations that are that in most places or in most workloads will work well. So we start with infrastructure, the number of our brokers, the instance types that we are using, the storage that we are using, the amount of storage that we are using, and definitely the traffic. Traffic part is definitely the hardest one to understand and also to reduce. We also have licensing, of course, if we are using a managed Kafka. So we have that support usage. If we are using a serverless type of Kafka, then it usually will be built based on the partition count, the read and write that we will conduct, and the static storage and operational. And in many places that I'm encountering of, the operational side is something that you put on the side, like the human hours, the amount of maintenance that we put on our clusters. If we're specifically talking about self-hosted Kafka, and that's a big chunk of the cost of the total cost of ownership that around Kafka. What makes it go up? So we start with some baseline. It looks awesome. Like we get a pretty decent Kafka cluster for like X amount of dollars, and we think that would probably be it. But with Kafka, in comparison to any other infrastructure component that I'm familiar with, definitely in comparison to traditional databases, it can grow exponentially quite fast, quite a rapid pace. And all of a sudden, like we can start with 1 month that cost X amount of dollars, and all of a sudden, like on month 3, once we open the doors for all the developers in the organization, all of a sudden it's like spiked and increased by multiple percentages. So multiple factors for that. Data volume, that would be the first one. Number of consumer groups. You should have a proper distinction between consumers and consumer groups. Don't forget that consumers within the same group will always read one unique message from the topic that they are reading from, but consumer groups duplicate that message. So quite fast we can multiply, and much more than that if we add more consumer groups to a single topic. The data that goes in will be multiplied by the amount of consumer groups that are connected. Throughput and latency requirements, as we strive for lower latency and higher throughput, that makes us to increase the number of brokers and definitely change their types into a much more robust brokers, more CPUs and more memory to boost performance. Usually that would be the case. Retention policy, again, one of the biggest factors for increasing our static storage. Number of partitions as a direct effect to both CPU cycles, CPU utilization, memory utilization, and static storage. And if we're talking about the managed Kafka of the world, partitions also creates a hidden charges, even in the serverless offerings.
I got one question here. Hello.
Please.
Yeah.
Yes, please.
When you talk about the data volume should be in the distributed environment or in the cloud environment or like NAT storage, like what particular data volume you are looking for here?
So data volume, amount of data that is being write or that is being written to our clusters, that would be multiplied exponentially by the amount of consumer groups that will read that data. So if we constantly writes the same amount of data, that yes, the cost factors from that will not change a lot. But as we increase the amount of data that goes into our Kafka, it will create a chain of reaction that increase costs across multiple factors just by increasing the amount of writes that we are doing to our clusters.
Okay, thank you. Just consequent similar question. If you want to ignore it. Like when we are working with the Kafka, the current event of the data we are going to write into the storage area. But once the data increase, then it has to go to the backup or the network storage. Then when you talk about the data volume, only the live data you are considering, or the storage data like 1 year's old data also you are considering?
Sorry, I'm not quite sure I understood the question.
Could I repeat my question once I just give a try?
Yes, or if
just
yes,
one
please.
second. Indrajit, I'll request you to type over the chat. Once he will take pause from one topic, he will answer that.
Okay, thank you.
Thank you. Thank you.
Thank you. Yeah, and number of connections. Number of connections usually users or Kafka operators tend to forget about it. Now it does. We do have in Kafka an automatic garbage collector or a timeout that will kill idle connections, but at the same time, we saw many cases throughout our research before building SuperStream, or throughout my experience personally as a Kafka user, number of connections when we are talking about large scale environments, if they are being shut down or killed at once, a large amount of connections at once being shut down, that can spike our CPU. And also, again, in some Kafka flavors, it can definitely increase our cost. So connections, we'll talk about in a second how to handle those. But number of connections it's again another critical another critical component to think about when we're talking about cost and what increased that. So how to optimize the big five? I'm not a huge fan of a lot of words, so I'll try to explain it verbally, each and every tip that we are seeing in front of us. So we start by setting appropriate data retention periods. And again, all the fives that we see, there are other tens of other optimizations that I can offer, or I can state as well. I think these five are the bigger ones for most Kafka flavors, and at the same time are the most common for most environments. So if you don't see all the optimizations that you're familiar with, it's quite deliberately. There are quite a lot, but I wanted to stick with the ones that are the most common ones. So setting appropriate data retention periods, usually what we see is that engineers put a single policy for all topics, like 7 days, all the topics 7 days, all the topics like 3 days, something like that, even though producers and consumers pretty much read the data as it flows into the topic. And then we might have a mirror maker that replicates the data. So we want to make sure that we don't lose any data because of the retention policy. So we increase the retention policy a bit. But from that into infinite retention policy or 7 days retention policy, that's something that usually we ignore, and there is a good chunk of cost reduction that can achieve just by modifying data retention again per topic individually and per use case. So it's crucial to profile each topic individually and understand its access pattern. Second one, and introduced quite recently. It was not made in the Apache flavor of Kafka. It was not delivered up until recently, and Victor will discuss that as well in his session. But tiered storage is a great compromise for reducing retention, to offload cold offsets to a cheap object storage. So if we feel a bit unsure about reducing our data retention because some connector or some replicator or something like that might occur on day 4 or day 5, it would be good to, again, not lower the retention, but at least activating tiered storage and make the proper calculation based on the profiling of each topic individually, and offload cold topics to cold offsets to hot offsets. We have some questions in the in the chat. Sam, should we address it right now or maybe in the end? We can follow them
Yes.
at the end as well.
Yes, that will be good. By then we'll be
Okay.
having more.
Awesome. Okay. JSONs. Ditch JSONs. Let's talk about it for a second. Usually when we think about schema registry, protobuf, and Avro, we think about the governance part of things, the data quality part of things, that the advantages that you get to increase data quality by converting or serializing your events into protobuf and Avro. I encourage you to think about it from a cost perspective, from the cost angle. So converting or serializing your events into a binary format, such as protobuf and Avro, will reduce up to 50%, in some cases even more, without jeopardizing a lot of the CPU utilization of your clients. So it can be great for data quality, but it also can be great for reducing your payload. So converting your events to protobuf and Avro, or basically any other binary format, huge amount of traffic savings. Locate inactive partitions and topics. That one is more, it's not just oriented for the, I can't say it's just for the managed versions of Kafka or the serverless flavors of Kafka. Partitions, a lot of partitions and topics has effect on your memory and CPU utilization and storage of your, not CPU, sorry, memory and storage of your brokers. And usually we tend to forget about them, but they are there and we don't have a timeout or a garbage collector for those. So that can greatly affect, if you're using a managed version of Kafka, reducing those inactive partitions and topics can greatly reduce your bill. If you're using a self-hosted Kafka like Apache, that can also help to reduce the internal compute resources of the brokers. And if possible, and that will sound a bit funny, but use a managed Kafka. And what I'm saying by that is, what we found is that the main cost pillars of Kafka is, yes, it's storage, it's amount of brokers, it's the infrastructure, definitely. But a large chunk of your total cost of ownership is actually the human hours, the management, the scaling, and a bunch of other things that in order for you to get, you would need to build yourself and maintain and put a lot of human hours. And that's probably the most expensive resource that you have in your organization. So if possible, a managed Kafka, self-hosted or not, we have different self-hosted managed flavors of Kafka as well. But a managed Kafka definitely can help to reduce the amount of human hours put in Kafka. And performance, I see that we are reaching to our time, so I'll try to be faster. Performance, what slows our Kafka? Slow and unoptimized storage, one size fits all, we talked about it. It usually, it relates, it has a direct correlation to human hours and time. We don't have enough time in large environments to go to each and every client and understand a client and resources in our Kafka and understand them, analyze their access pattern, to profile them. But the one size fits all configuration literally is like one of the biggest or major performance performance concerns, or the things that slows our performance. Unoptimized producers and consumers, usually like, and that's sometimes surprising folks. Unoptimized producers and consumers actually are your biggest bottleneck, and not Kafka itself, not the cluster or the brokers, but actually unoptimized producers and consumers. and underutilized resources. So I try to be very brief here. You can gain 2-digit percentage of performance with just these following tips that you're about to see, from brokers to producers to consumers. So broker, if you're not using a serverless flavor of Kafka, so first of all, ensure that you are using a high velocity and local type of disks. SSDs and of course NVMEs would be the most preferred ones. Adjust the heap size to better match the memory capacity of your broker. That's a bit loosey or vague. It needs to be tested and really understand what would be the heap size that is perfectly match your workload size. But that can greatly affect your broker performance. Tune and make sure that your broker garbage collection is using G1 GC. That's the latest, and probably that's the latest, and probably will be great for all Kafka clusters. I mean, ever since version 2.x. So make sure to use that garbage collector. For AWS users, use Graviton instances that can reduce your CPU utilization by up to 38% and memory utilization by up to 57%, according to, first of all, our benchmarks, and of course, other users that did that change. So Graviton instances greatly affect your cost efficiency and also performance, and decrease idle connection timeout. Don't let them pile up and then killed at once in a large number. Producer configuration. It starts with profiling and segmenting your topics and their clients based on message sizes, throughput, durability, and read. Now, it is a heavy lifting. It does require a research and a lot of work. But at the same time, if you really want to achieve a substantial performance increase, you need to do that individually for each topic and its client. And then once you have those results and profiling and the profile of each every single topic and its related client, then you would be able to define a dedicated aux and batch size and linger MS parameters or values for each of those categories and groups. Last but not least, consumer configuration. Adjust the number of consumers in group. That usually adds, it's sort of like a thread pool. That's the way I consider a consumer group, a thread pool. If you add more threads, that's definitely helpful for the scalability of reads from the same topic. Adjust the fetch min bytes parameter. There is no silver bullet here. It can be higher, it can be lower. There is no single accurate value to either, and in most cases, default value, I see it as the wrong parameter for most cases. So do some experiments there, and if possible, prioritize deserializing data over decompressing of data. Usually, because we don't want to get into the heavy lifting of protobuf and serializing data into binary formats. We will usually stick with client level compression, which is the easiest one to gain. But at the end of the day, you will pay for it in the latency, in the added latency and CPU utilization that you would get on the decompressing side, while you can have both worlds by deserializing the data, which is a lot easier method to use for reducing payload size. Not easier, but definitely a much more efficient. And make sure to continuously adjust those. Now, we went through the different optimizations, the different tips, but the real challenge is to ensure that we always adapt ourselves. We set up a good monitoring. We always make sure that we continuously experiment and make sure that we adapt ourselves to the changes. Sorry. phone call just end. And then enforce configuration governance. Enforce configuration governance, that takes care of the proactive side of things. So we don't want to get to a point where our environment is already dirty and damaged. We want to make sure that we don't get there in the first place. That's why we need configuration governance. And last but not least, get yourself a good set of automation to help you maintain and operate the entire environment during peaks, but also during standard times. That would definitely help to reduce the human hours and make sure that you constantly adapt to the existing situation that your cluster is sensing right now. Thank you. Would love to have any questions if any.
Thanks, Senevia. We have few questions in chat. Do you want me to read that? We have a question from Indrajit. When you talk about the data volume, are you consider live data or live data and old data also? Many companies store the data in their storage device like NAT.
Yeah, so I mean, definitely I'm talking about both live and old data. If we ask it, like old data, by the way, that's exactly correlates with the retention and tiered storage that I'm asking. If you put old data, imagine that Kafka is an expensive component. If you have, and you know that you have old data that is not going to be consumed or to be used, then Kafka would not be the right place to store it. You should definitely consider offloading it to a cheaper storage component like S3, for example.
Thanks, Sunil, for the answer. We have a next question from Daisy. Can we make the expiration of data immediately after processed by consumer?
Expiration data, I assume we're talking about retention policy. If we're talking about retention policy, then it's not really related to the consumer or after processed by a consumer, we can modify our retention policy in any given time for any topic, despite the fact that it's ongoingly being written or read right now.
Okay. Thank
how
you.
can we effectively measure the access pattern for different topics so we can ensure we're not over-retaining data and overspending on storage? First of all, if you have a consumer leg, a consistent, if your topic in some given time in a month suffers from a consumer leg, sorry, that means that you need to take that under consideration when you modify your retention policy. And so that would be the first thing to take under consideration. And the second thing is to like really understand the business logic and how your consumers read data and how often read data from an existing topic. Again, as I said, in some cases we would have like a topic, we would have a topic that consumers are constantly consume data from, and all of a sudden, like on day 3, on day 4, and day 5, for some BI reason, some connector goes in and take data from like for Cassandra or SAP or something like that, and therefore we cannot afford ourselves to lower the retention more than that. So it's really depend on like the business logic and also the performance of your consumers. That would be probably the metrics. And I saw that Abhijit answered Sunil and Prachi. What network-related optimizations you suggest between clients and brokers? Network. If you refer network as traffic, then the number one thing would be to reduce your payload. It can take place through client level compression or payload reduction payload conversion using a conversion from a non-binary format to a binary format. That means converting your JSONs into protobuf or Avro. That would be the biggest optimization that I would put my time on. And last question before, maybe because we're a bit late for Victor, and I apologize for that. What advantages you see for managed Kafka over self-hosted Kafka, what to keep in mind while considering various solutions, offerings for managed Kafka. That's a long discussion, Amita, and I would love to answer that. Through email, and maybe afterwards. Please feel completely free. I'm writing my email in the chat, so everyone would be able to also send questions to there. It's a longer discussion that I can answer right now, but I would love to help out through email. And can we make the expiration of data immediately after processed by consumer? We already answered that, so definitely. I hope that I was able to educate a bit or give some good tips from my knowledge and experience. And thank you very much for listening and staying with us.
Thank you so much, Yaniv, and thanks for sharing your email ID. I'll request people, whoever questions could have not been answered because of time limitation, please reach out to him directly. He will be happy to answer. Thank you.
Yes.
Request Victor to please take over from there. Thank you.
Okay, thank you. I shared my screen, so let's start with the presentation as well. I prepared a demo too, so I will do some magic with the screen sharing later. So so my presentation will be about tiered storage, the integration with tiered storage. We look into it in more details, and with a side dish of Apache Iceberg. It's a quad side dish with this in this hot summer day, so I hope you'll enjoy it. But you can ask questions, of course. At the end, I will try to answer them. My presentation is a little bit long. I fit in 30 minutes, but my more slides because both tiered storage and Iceberg is huge. Well, we could from about Iceberg, I guess there are several hours of presentations online, and I tried to summarize them in a few slides, which can be a bit dense, but so we'll start with the two architecture types. I wanted to put tiered storage in its place in a bigger scheme, or from a big high point of view, and we'll reiterate the classical architecture types that we have in the big data world, which is the Lambda and the Kappa architecture. Then we'll talk about the importance of tiered storage, and at last we'll look at how the operational and analytical worlds are connected by components, and how you can connect Apache Kafka with Iceberg. And with a simple architecture. So So what is Lambda? So Lambda architecture is the classical big data system layout, where you have two flows. Typically, your upstream clients like sensory data, I don't know, flight bookings, financial data, IoT data, whatever you have is directed into either a stream processing system like Kafka, Flink, Storm, or a batch processing system, which was the classical Hadoop, MapReduce, or Spark lately. And the result of these systems is stored somewhere in some kind of data store. With Kafka, for instance, you could have connectors and all that stuff to store your data in cold storage. And similarly to this, the batch processing systems also store their data on HDFS, S3, and all kinds of these cold storages. And this is what we call data lakes. These are the loosely defined data that we collected from many places. And we put some serving layer on top of it, which will serve your downstream applications, be it real-time applications or batch applications. These serving layers could be like Apache Hive. And this consists of two flows, a stream flow and a batch flow. Now, when Kafka came up, it also defined a new way of looking at the architecture, a simplified view, where you have only one flow, which is stream processing. All of your upstream clients are channeled into the stream processing flow, and all your real-time application just reads from or batch application reads from a topic. It might use some simpler frameworks like Kafka Streams, or more complicated one like Flink or Spark to process this data, save it back to Kafka, and yeah, this is the practical example of this operational database or operational implementation of a system. And now it comes. So as Yaniv mentioned as well, tiered storage came into the picture a little while ago, quite recently. I mean, yeah, quite recently, not a little while ago. So this made it possible for Kafka to store infinite amounts of data in cold storages, in object storages, or remote file systems. And this made it possible to eliminate all that other processing frameworks, since you didn't need to put a serving layer on top of it. You can just consume from Kafka and produce to it. You may have some stream analytics or stream processing solutions like Flink or Spark to transform your raw input topics and make it available in a different format for your applications. And talking about tiered storage more, so what is it? It is basically splitting the storage of Kafka to two parts. So you have some local disk where you store like a few, I don't know, gigabytes, hundreds of gigabytes data, depending on use case, on your use case. We'll see that you can also optimize it really well now. And on the second level or second layer, we have an object storage which stores the rest of the terabytes of data that you have for Kafka. And whenever a consumer or producer, reads it, it caches back to the brokers, and you can read it more and store it more efficiently. But talking about the benefits, so I split this into three categories. The first one that you get is operational simplicity. So thinking about if you have a cluster that you need to rebalance because of some operational reasons. For instance, you added a cluster, so you need to upscale, or remove the broker, so you need to downscale. Then replicating is much easier because you store much less data on your clusters. Or in a failure scenario, you will get shorter recovery times. So when a broker fails, you have to either fail over to another broker because that failed one went out of business permanently. So you need to reassign partitions, move partitions to a new broker. Or when the broker starts up, then it has a load time for it. It has to read partitions, re-index them if that is lost, and that can take a lot of time, especially when Zookeeper was used for Kafka. But with tiered storage, you store less data. It means less log segments to recover, and brokers are faster generally. So if you want to take Kafka into the cloud and maybe use a managed Kafka, then you will, as the implementer of that, you will find these object storages very useful because they are integral parts of the cloud ecosystem. They are cloud native. They are always there, and they are very cheap compared to block storages. So it's worth using them. I did a couple of calculations on Amazon, and it comes down, if you take the fixed amount of a couple hundred megabytes, it comes down at least 50% or even more in most cases. But you have to calculate this for your use case, but usually it's a huge reduction in cost. And the third one is, which I already talked about, is the Kappa implementation. You have unified clients, you eliminate the batch workflow with this, and you don't need to use different kind of applications for different kind of flows. You consume from topics and so on. It's also scalable. So one thing is the storage scalability, which we gained with tiered storage, but the other thing is that the compute scalability, which we gained with KRaft. So with Zookeeper, we had several problems with huge clusters because it needed to propagate metadata, which wasn't really effective. But with KRaft, it's much better. We can scale into the millions of partitions, making huge clusters with tens of terabytes or hundreds of terabytes of data, or even petabytes, as you may see in Uber's use case or LinkedIn's use case, really feasible. And Kafka is really grown up to do this job with this. So I don't really want to go into too much details with the storage, but just wanted to take a look at the high-level architecture, which is useful to understand if you want to configure it. And if you want to configure it. So in the white rectangles represent what we had so far with Kafka. We had a replica manager, which handled leader elections and handled the log managers and appends and so on, where the log managers would handle cleaning log segments and also the log segments themselves, cleaning, deleting them, creating new ones, and so on. And of course, we had the local log segments. Some number of archives log segments were closed, and an active one, which was the tip of the queue or tip of the partition. And these are all stored on local disk. Now, the tiered storage feature introduced a remote log manager, which is a periodic process that will take your local logs and save it out to your remote object storage. This log manager also handles this remote storage manager and remote log metadata manager, which the first one, the storage manager, is responsible for communicating with the remote storage. And the second one, the metadata manager, is responsible for storing and retrieving the metadata for the remote segments. They are separated because it is shown that Kafka needs metadata more often than log segments themselves. Just, if a consumer wants to fetch, then it has to first look at the metadata. Where does it find the given segment, given offset that it wants to fetch from, and therefore we need it much more. Yeah. And if we would store them together, it would not be that efficient because get and put operations cost you money on object storage. Therefore, it was separated, and in practice, this log metadata store is a topic, a Kafka topic, a replicated Kafka topic that store these index files. So let's look at the demo, and I'll quickly stop sharing and share my IntelliJ if I can find it. Oh, well, I just shared desktop. Yeah, so, okay. What we have here is an ugly git ignore file, which we are not really interested in, but I used a Docker environment to configure a MinIO storage and Kafka. This MinIO is a S3 compatible storage application, and it is very good in doing these demos. So that's why I used it. In my Docker file, I just simply configure it, and I also create a bucket, a similar bucket that you would use in S3, and this is what I will use with Kafka. For Kafka, I have a single broker implementation. I used Craft as this should be now the norm instead of Zookeeper. I didn't want to create like more brokers because for demonstration purposes, I think it's perfect to have really one single instance, and it demonstrates more new capabilities of Kafka now. So looking at the configurations to see how you would configure tiered storage, we have a Kafka. Bit back. So this image is the official Kafka image. And what you do here is you pass on the Kafka configurations as environment variables. So if we take a look, this is, I don't know how many of you have configured Kafka so far. I would think most of you. So what you would have to do is configure the listeners. In case of Kubernetes, not Kubernetes, but Docker, since they run on a separated network, you have to configure advertised listeners. I configured the process roles here, and this instance is a broker and a controller combined. And for that, we configure the quorum voters set, which is, again, this single broker is the quorum controller and the broker together. I have configured listeners, one for the controller, one for the communication, external communication, and the internal one as well. And I configured the replication factors, single replication factor for now, not just because it's cost effective. You shouldn't do this in production, by the way, but because I have one single broker, you can't have more replicas. Yeah, anyway, I tweaked the retention periods to enable like really small logs, really short retention checks. So what we do here is seen instantly in case of tiered storage. And by the way, I will start my application because it takes a little bit of time to see them in the object storage. So, and you can see it is started. You will soon see, hopefully, that it produces megabytes of data per second to the storage, and we'll leave it here so it runs for a while I'll explain the tiered storage configuration. So yeah, and we arrived to the tiered storage config just now. The tiered storage Kafka itself doesn't give you an implementation. It has some really dummy implementation, one that you can look at as an example, but like more advanced, like S3, Azure, GCP implementations are missing from Kafka. For that, you will have to find a provider, and what I could find so far, and I think it is the only one implementation, is Avon's tiered storage plugins, and that's what I used. I don't know if someone knows if there is something else, then I'm happy to take a look at them. But yeah, I heard that Uber also wants to open source one or two of their connectors, but I haven't seen them so far. So yeah, how do you enable it? Simply, you will have a remote log storage system enable flag that you will set to true. Again, I lowered this log manager task interval to 5 seconds, so it every 5 seconds it will checks for log segments that can be saved to the remote storage. And I'll stop this now because 1 GB of data would be enough for use case. Yeah, and yeah, I configured the remote log metadata manager here. This is what the one I mentioned is topic based, and this is the default as well. It's just here for explicitness. And then I configure some implementation or plugin specific configs. Well, this is this first two is not that yet, because the two things that you have to give to your to Kafka is First is the entry point of the remote storage manager. That is the implementation of the log manager of your choice. And the second one is a class path where you find the jars of the plugins, and the class loader will load that and instantiate this log manager, and will, of course, read up the other configs and we'll start to use it. So what I have here is a couple of A1 specific configs. These are for chunking, fetch chunking, so it won't retrieve the whole log. When you consume it, it retrieves chunks and it caches them. So I configured that. And also I had to configure the storage backend, that is the S3 or MinIO config. These are the same for S3 and MinIO since it has a compatible API. Here again, I needed to configure a backend class that handles the storage and all that kind of S3 related configurations. And that's it for sorry, one more thing that is important, that you don't just have to configure it system-wide, but you will, when you create a topic, you would also need to do some configurations. And in my code, what I do is I create simply an admin client. Here I'm just using Kotlin to create a topic and produce to it. I use an admin client with some properties that are fitting to my Docker environment. I list the topic, and if the topic doesn't exist, then I create a new one, and I pass some configurations to it. And these three configurations are: the first, I enable remote storage. That is, the topic will be available to the remote storage, and I set the local log retention time and the local log retention bytes. These are important for us for the demo now, because we don't really want to we don't really want it to take a lot of time to copy segments to MinIO. So I set this to some short 10 seconds and 10 megabyte values. And in my example, what I do is here I just describe the topic to assert that it really was created, and I use a random generator to generate random purchases of some kind of retail store and push them into Kafka. It is really simple. It has a user with name, email, address, phone, username, so on, a product which has an ID, a name, and the price, and the purchase that combines the two, and and adds an amount on top of. And I really just create a stream of it and produce this random generator creates a stream of it and produces to Kafka. Now let's go back to Chrome, and I have this MinIO console, and I just wanted to show you how it's saved. So you can see that it produced 100 megabytes for now. It is a bit slow, to be honest. I could have used a better configuration, but yeah, Kafka might still save data back to MinIO. So that's why you see only 100 megabytes, while my application said that it's already produced 100 gigabytes. But anyway, it will be there. And also MinIO is a bit slow in refreshing this data. So in the bucket I created with Docker, I have a tiered storage demo folder, and in that I have the topic, and in that the partition, and within that the segments. This is very similar to what you would see in the file system case. Only strange thing you could get is like I have 1 megabyte segments because, as I said, I set it to a low number, so we'll see it sooner for the sake of this demo. Okay, so let's go forward. I'm also a bit short on time. as anticipated. And let's take a look at the other side of the table, and let's compare how analytical workloads are different from operational ones. So what we had on the operational side so far is this. We had a Kafka instance. Well, in my example, we didn't have Flink because we didn't have to transform records, but you can easily imagine it's there. And we had batch applications, and well, we had a real-time application for now, that producer. And so what are the differences, and how does Iceberg come together with Kafka? So in the operational world, what you do is you basically enable your business's operation. You have custom clients like microservices, downstream applications that enable your business's day-to-day work. As Yannick also mentioned, we use in the streaming world row-oriented data formats like Avro, JSON, which we learned you shouldn't, or protobuf. And we also think of these streaming applications in an event-oriented way. So what this means is we have upstream events coming in, like a sensory data triggering, being consumed into a topic which will be read by a microservice, which this incoming data triggers the microservice, therefore, and we just really think of it as an event-oriented application. And on the other side, for the analytical workloads, what we see is that what we want to do is improve our business. So often we employ AI or ML model training to get insights of our data. We often work with column-oriented data stores, which use more efficient formats like Parquet, and we often think in statistics. So one record is not a trend, one record doesn't matter, but 1 billion record matters, and what does it show to you matters. Connecting them, therefore, is hard. You have different formats, as I mentioned. You have different mindsets, and really what you would do is really different in the two sides of the world. Now, okay, I forgot to change this slide. Sorry, the title. This is Iceberg. Editing on the go. That's what I like. Yeah. So yeah, what is Iceberg? So it is practically an API and a set of libraries. It is a table format specification designed for efficient data lakes. And in practice, and we will see some of it, is that you would use Flink and create Iceberg tables that would save data into Hadoop, into S3 in a specified format, and that format is specified by Iceberg, and it is designed to be more efficient than Hive, for instance. And what it is not, so it's not a storage engine, it's not any kind of implementation of object or block storage, so it doesn't define how is, I mean, it doesn't define things like you would see that like S3 or again Azure, these kind of object storages or block storages like EBS. It's not an execution engine, so it cannot like split the query into chunks and execute it as it wants. That is done by Flink or Spark. It's not Iceberg's job. And it's not a standalone service. So as I said, it is just a set of libraries and APIs that you would use in Flink and Spark and software or components like that. And how do we connect that? The previous slide was a bit of a giveaway because I said that Flink and Spark would use Iceberg. And yeah, this might be a bit misleading that I represented this as a separate component, but really it is a library. So what you do here is you read from Kafka, process with Flink, save it to Iceberg, and you again on the data store, you can use that data wherever you want. You can create reports, train ML models. There is a whole different world there. And you could always also use Kafka Connect now, which is maybe a bit simpler to use. And well, I mean, you can do some message transformations with Kafka Connect, but not as complex a thing as you would do with Flink. It's just rather like for simple things is good. So I would have a demo, but since operational and analytical workloads are hard to connect, I unfortunately couldn't really expand my previous demo, what we've seen here with Flink. For some reason, I couldn't really configure Iceberg with Flink. Maybe next time, I will. There is a lot of lessons in that as well. How would you set up a Docker environment with Flink, Iceberg, and Kafka? In my demo, which I uploaded already to GitHub, separately they work, but together they don't. I mean, Flink and Iceberg. Yeah, I will fix that. Unfortunately, I didn't have time for this demo. So what I wanted to do, so what I wanted to do, I created or extracted the gist of that stuff to here as well. I wanted to create a source table with similarly for this retail use case with a simple source table for Kafka. This is a Flink query where you have a event ID, a user ID, and the dollar amount that was purchased by that user. This is a single purchase. And I wanted to create a sync table in Iceberg with a user ID and the total amount that was the total amount purchased by that user across several purchases. And in Flink, you would be able to just a bit staying with this, you can see that in case of Kafka, with the with statement, you can specify the data source or sync and really just latch onto a topic or latch onto Iceberg and really make a bridge between these two systems. And with a single query, you can insert into this total purchases sync Iceberg table by selecting the user ID and summing the amount in the Kafka topic and saving it in the total amount that is the Iceberg part of it. And you just group by user ID, and that should give you the results that we want. So yeah, I'm a bit out of time. Sorry, I just have 1 or 2 slides. So what are the weaknesses of this architecture? It is that we have extra costs still. Kafka has to, or Flink has to read from Kafka and save to Iceberg. And you have to process the records, transform them from Avro or whatever format to an Iceberg compatible that will be Parquet. Then you have to be, if you want to process a lot of data, then you might potentially set it to an early offset and process like, I don't know, tons of terabytes of data, which is not really ideal. And how we can fix this? There are solutions out there. Well, not every, but many companies working on this, like Confluent has this Tableflow, which can connect Iceberg and the Kafka. They presented it recently in the London Kafka Summit this year. And but also the community has started moving this way. This is a proposal by Uber as well. And similarly to Tiered Storage, they want to take this further and marry Parquet and Kafka. And what we see here is the classical way of how the producer, the broker, and the consumer works in today's world. So in the producer application, in step 1, we encode our data with Avro. In step 2, step 3, we batch it up, compress it, and we send the compressed segment in step 4 to the Kafka broker. In the consumer application, let's see the ingestion consumer application that is on the top. We would, in step 1, take the data, decompress it in step 2, and then decode it into an Avro format in step 3, transform it into a Parquet format in step 4, and in step 5, send it to the data lake. Or in our case, you would just, instead of transforming it to Parquet, you would send it to Flink, and that would transfer it to Iceberg and would end up in the data lake. But this is a kind of a simplified view. ASCII 1008 or this Parka defines what ideally what we would like to do is, instead of encoding and compressing, really just by start doing all this stuff in Parquet. So the Kafka client would collect the batches, encode them into Parquet, and this Parquet segment would be transferred over the network and would be stored in Kafka. And the consumer application would read up these Parquet segments and transfer it to the data lake where it could be processed. This doesn't involve Iceberg and Flink and any kind of data transformation or any kind of middleman. But in this case, the flow would be that later on you would read up that data from the data lake and process it. So it's a little bit of a different flow. And with this, you could also save, according to their presentation, that was also on the summit, like 10 to 30% of networking and storage costs. Also, you could save tons of processing costs, as you don't need to encode and compress and decompress your data, because Parquet is in itself efficient, and also it can be compressed. Yeah, but you don't have to do that back and forth between compressing Avro and then decompressing data. So this is all I wanted to talk about. So thank you very much. I hope you had some insights. And the example will be is up on this GitHub address if you want to take a deeper look into it and see how it works and how you can configure the storage. So thank you very much.